Hi everyone. Last time we did set up the parametric analysis, and now after quite a while it has been finished. There were some problems, so I had to redo it. In the same way, the computer actually restarted, so you can see the execute command section is a little bit different than what we did in the last session. But we did almost everything the same. We gave the modification of cases for example, if I show you edit, and it takes a while to load everything. Yeah, so the original settings were initial settings, and then we moved to 1 volt, 0.9 volt, zero point 0.8, 0.7, 0.6, 0.5, and then back to 0.7. We didn't go for zero point 0.4 in this, and there wasn't a problem with this. At zero point 0.4 we can go to 0.4 also, but just to save the time, uh, I did like this. And how to see if our modifications are being correctly done? So the first thing that we should check that if our modifications are correctly encountered are like this. So if you go to the voltage section and see that this was the OCV for 50 iterations. At the initial conditions it was run for 50 iterations, and the voltage is stagnant at 1.1. This is the almost OCV 1.107, and then we specified the voltage condition for 1 volt, 0.9 volt, 0.8, 0.7, 0.6, 0.5, and then we return back to 0.7. And from the scaled residuals you can see that everything was converging, but in the real solution we shouldn't be limited to 50 iterations. We should give at least 100 or 150 iterations, maybe 200 also, depending depending upon the extent of accuracy that we desire. Right now this was just to show the how to do the parametric analysis. So 1x 1 minus 1 is really not acceptable. It should be at least in this order, so our continuity is not properly converged. So we should have given at least 100 iterations or maybe 200 to get a proper convergence at every point. So but the demonstration can be easily shown here. So, and the current on taps, obviously this is the final result for all the current on taps result, minimum mole friction and utilization. So now we will go back to the contour plots. Contours of it should be contour of mole friction. Okay. Okay, now what we did was that during the execute commands we saved all the contour plots using two different ways, using an animation method. So if you go to solution animation, we saved it using solution animations, and we called it plot o2, and all the contour files are using, so we saved it all everything in the working directory. Now the label that I have given in here, for example, if I go to pick temperature, and it will save it by the name contour temperature. So the commands that are using the file name with contour are actually saved using the execute commands. And from the solution animation, if I go to temperature, so it's being saved with the name of plot temperature. Now if we go back to the working directory, we will see that there are file names that are being saved with contour names and file names that are being saved with plot names. And the difference, if we say the difference between them, is to mole friction at initial iteration. So see that now there is no mesh, we couldn't draw the mesh, but if we go to the same h2 plot in the contour side, so we go to the contour, and at first 50 iterations we take it, and you see we got a very wonderful picture of the contour plot showing the inlets and outlets. And if you go forward, this is at 100 iterations, keep looking at the name. So keep focus on the name. So this is at 100 iteration, then 150 iteration, 200, 250, 300, 350, 400, and then it will the last one is actually because we know that the iteration number 400 corresponds to what condition. This is an important thing that we should keep in mind, and that is the reason we have the report plot file. And in the report file we can open it using the Excel program. So we will open it using Excel. Just a moment. I need to log into my account and access it. So yeah, now we open this file using the Excel program. So we can directly go to the open and browse. So we will browse it into the PC in the research work, rectangular simulation, and the guidebook chapter. And this I already know it is in the project videos files, dp0 fluent 1, sorry, not fluent 1, I think it is fluent. The working directory right now is fluent 1, fluent, and here we should show all files. Or yeah, here we should open the report file. Now as we did before, like in the previous sections also, so we will do the same way, and backspace text qualifiers, finish, and we get all the data over here uh, arranged in order from with the iteration number. And here we can also plot the IV characteristic curve. It is not fully converged, so we are getting wrong fuel utilization values. It's not fully converged, but just for the sake of demonstration it will be okay. We get the temperatures, and it is important that we included the mass flows at the anode side and the cathode side. Why was it important? Because for the parametric analysis, the next step is to change the mass flows of anode and cathode to get the optimum temperature and fuel utilization. So we will be changing the mass flow rates. So right now this is constant, we didn't change it, but the same way we can change it using the text commands for so setting the boundary conditions at the inlet and outlet, sorry, at both inlets, at air and hydro anode side and cathode side. So now we will take, because we know that the fully converged solution is at every 50 iterations. So this is converged solution, this is a converged solution, like for this demonstration only. It's not fully converged yet, and 200. But the important thing is that we can see the cell voltage. Now the cell voltage over here is 0.8, and then it went up to 0.5 and then back to 0.7. So at the iteration number 400, it's actually a voltage of 0.7. So bearing that in mind, here when we see the iteration number 400, that means it corresponds to a cell voltage of 0.7, but the figure at 0.35, so that means if we want to make an animation, we will have to like stop at the iteration number 350. And that the same thing goes for all the other control plots also. So if you go to the control plot of for O2 mole fraction, so O2 mole fraction, you can see the changing, the variations that are visible, especially in the return marked it as global. I just made the local one right now, and you can see 300 and 350, and then there's a sudden change back again. So you see it goes to 0.09 and then back to 0.14. So we will exclude the 400 for the purpose of animations. And now you can see we have all the contour plots, and we can select them at different conditions. So this is the one of the most important part for the post processing. So, and that was automatically done when we were doing the parametric analysis. Especially now we can't get these pictures after we have done the analysis. It is really difficult to get back at a condition of 0.5 or zero 0.8 or zero 0.9 volts, but here we can get all the control plots along with the final desired solution at 0.7 volts. And yeah, we can see, but in the plot, so when we make save the pictures using the animation tool, so here now observe that there is no, we were not able to draw the mesh. It can make a proper animation, but drawing the mesh will be difficult. So if you see that it is being changed, changes are visible, but there's no for the plot, for all the file names that were saved using the animation tool, they were named with plot, and there's no mesh shown or the outline of inlet and outlet shown. So this is one drawback of using the animation tool, and by using the execute commands we can accurately make our desired images or the contour plots. The same way for the animation, we are rolling the animation. For making the animation, we just take the images after at each time step, or not time step, at each convert solution, for each convert solution, and then using those images we make the final animation. But the same can be done by using the execute commands. Now we will go on and see our characteristic curve. So for the characteristic curve, we can copy all the convert solutions and control C, and let's paste over here, and paste them over here. Okay. A better way was to copy this sheet entirely and then delete the unrequired rows. And now here we can actually plot the IV characteristic, but for the IV characteristic it is important that we have the current density, not the actual value of current, although it will be same. So we need to have an area. So if active area is a active in centimeter square, so this we can actually compute from using the Fluent. So if we have the calculations for this, we can actually make a report definition. So if we go to our report definition and set a new, and we will have a surface report area, and we will actually call it active area or area active, and here we will check the area for wall electrolyte anode or cathode. So if you compute it, you see meter 0.000361 meter square, and it actually doubled it. Yeah, it's the same. Anode or cathode, it's the same thing. So we'll say okay, and this is the area in meter square, 0.000361. So you copy this here and go to the Excel program and give this value. We can change the units back to meter square, or we can change this value to centimeter square or meter square, so that's okay. So it's the same, and here we will get current density. Now obviously it will be in ampere per meter square, ampere meter square, and we should actually have this in text wrap. Now this is equal to, and it is important to note that the actual current value, although they are really same at current tap and voltage tap, but just at the initial value it is mainly the voltage tap that is giving the current, and we got the voltage from the cathode side. So we'll take this value and divide by the active area, and we'll get the current density in ampere per meter square. Now we are ready to set the IV characteristic curve, plot the IV characteristic curve, and here we don't want to include this value, so we will select till this and control this, and we will go to insert scatter, and we want to switch row column. Okay, no, cancel switch row column, want to delete it, remove it, add series name IV characteristic, IV characteristic, and the x values are actually the current density, so this is the current density, and the phi values are the voltages. Okay, so we get a very beautiful IV characteristic curve. We need to still compare it with the desired result, compare it with the experimental result, and I think using the same procedure we can have plotted on the same curve. This depends upon the research geometry and all other things, on the type of selection of experimental data and other things. So the experimental data you can choose according to your own geometric model and other things. So with this we can conclude that we have plot the IV characteristic curve, and we also got all the control plots which were saved. So with this the post processing is also automatically done at using the parametric analysis, and if you want to process further any results at the desired condition at 0.7 volts, so now we are already at 0.7 volts. So if we want to get more data or temperatures, velocity control plots, pressure profiles, and all this data we can have at this condition. We don't want all the data at all of the points. If we want, we can have them in the execute commands, or in you can also have plots, report plot files, like we have report plots. If we want to have average velocities or pressure drops, we can make report plot files and save them also in the in this report file. And this way these variables will be stored for all the conditions. So here, like, we have the fuel utilization, temperatures, and minimum mole fractions. So that way we can have the pressure drops, temperature gradients, main velocities, and all these conditions also. And if we want to make additional control plot, then we can have for velocities, we can have them in the execute commands. This concludes this session for the post processing of the results, and we got all the contour plots, as I showed you before, that we got all the contour plots also here in the project videos, DP0 Fluent 1, and we got all the contour plots also. So we can make the animation if we want, and we can use any animation tool or websites to create GIFs